And well, hello, welcome to 120 Zoom session for March 19th, 2019. Oh, it's been a little while, a couple of weeks. You had spring break before, so now we meet again. Now, the last Zoom session that we did was actually 2 weeks ago on March the 5th. And I believe then what we did was a review of the outer and the middle ears. And that Zoom session I uploaded onto, I believe it was Unit 3 on the middle ear. But really, the week before that and the week before that, we were on the inner ear. Okay, so we were a little bit ahead. We were ahead in this time. So what I'm going to do today is kind of review stuff of the inner ear. And we'll look at the anatomy and make sure we're up to snuff on the anatomy. And then we'll push in a little bit into the physiology. So what we're doing is bypassing the review that we did on the middle ear on March 5th. I'm looking at the calendar here, yep, March the 5th. And we're going to talk about what we spoke about on the 2 weeks prior in February. I believe it was February 26th. If I can kind of take a look, see, it would be February 26th, and I believe, yeah, February 19th or something like that. So those two were on the anatomy of the inner ear. So we'll look a bit at the anatomy of the inner ear. I'll share screen with you here. And we are here. Okay, inner ear anatomy. Make sure, let's just make sure we know, whoa. I don't know what always happens with that. I don't know why that happens. Anyway, well, okay. Make sure we get our ducks in a row here, okay? Bony and membranous labyrinths of the inner ear. The vestibular system has them and the cochlea has them. Okay, showing a picture over here, making sure we've got it. All right, looking here, big time. Okay, all the white is solid bone. This would be a right cochlea, because the front of the cochlea, the tippy top of the cochlea, is aimed toward the back of the eyes, okay? And the vestibular system here in pink, that's actually more lateral to the cochlea. The cochlea is more medial. So you can tell that this is a right inner ear, because the tip faces the back of the eye, and the vestibular system is more out toward the ear, okay? So oval window, round window. You can see pretend the white is solid bone all around petrous portion of the temporal bone. And then this brown area here would be the bony labyrinth, and the pink area would be the membranous labyrinths of the vestibular system. And in the vestibular system, you got the three parts: the utricle, the saccule, and the three semicircular canals. And you all remember that the sense of balance has three pieces to it: the vestibular system, vision, and that thing called proprioception, knowledge of where your limbs are in space. So then you are looking here at the cochlea. It too has a bony labyrinth, which is drawn in yellow, and the membranous labyrinth happens to be drawn in orange here. Now remember, the vestibular system and cochlea are joined together. So the bony labyrinths share the same fluid, and the membranous labyrinths share the same fluid. And we all know what that fluid is called. The bony labyrinth fluid is called perilymph. The membranous labyrinth contains endolymph. All right, looking at the sensory areas where the hair cells are, in the membranous labyrinths of these two, of the vestibular system and cochlea. Membranous labyrinth, especially of the cochlea, winding around, okay? And we looked briefly at the vestibular system. The hair cells there could be type 2 or type 1. All right, remember, type 1 is afferent, type 2 is efferent. And in the cochlea, inner hair cells are afferent, outer hair cells are efferent. Again, showing a type 1 and type 2 cell close together. Type 1, shaped like a pear. Type 2, shaped like a test tube. And we don't need to go too much into the vestibular system here, because that you can always look at the previous units that we covered, previous Zoom sessions on that. So no need to repeat all of that. We'll just move through. Showing you the bony labyrinths and the membranous labyrinths. Okay, making sure that we've got these things oriented here. And then looking at the membranous labyrinth, how it's actually triangular in shape. Recall that? All right. And that triangular shape is actually the scala media. Scala tympani, scala vestibuli, scala media. Showing you just the membranous labyrinths here and how the eighth nerve fibers leave the membranous labyrinths of both the vestibular system and the cochlea to join on as the eighth nerve carrying to the brain. Note well that the seventh facial nerve, the one that innervates the stapedius part of the acoustic reflex, it runs right alongside of the eighth nerve. Now, in a couple of weeks from now, we'll be talking about retrocochlear pathology and how that, when the surgery is done to remove a tumor of an eighth nerve, often the seventh facial nerve is compromised as well, leaving the person with a bit of facial paralysis. This can often happen with eighth nerve surgery, but we'll cross that bridge when we get to it. Know well and know now that the seventh cranial nerve goes through the same tunnel of bone called the internal auditory meatus from this area here toward the brain. This is the cross-section of the cochlea, of a cat's cochlea, but nonetheless similar to a human cochlea. Widest at the base, narrowest at the apex, but take good note here, the scala media is actually smaller here and gets larger toward the apex. The same is seen in an unrolled cochlea. The scala media actually gets wider toward the apex of the cochlea. More mass, less stiffness. Same shown in a cross-section of a cochlea. All right, so note that the scala media gets wider as you go toward the narrow apex, exactly backwards to the way you'd think. Look at the light blue areas, taking a good note here. This is the organ of Corti. Tectorial membrane on the top, basilar membrane here, Reissner's membrane here, spiral ligament, spiral lamina, spiral ganglia. 3 spirals, remember those? All right. Lamina, because it's it's got layers like laminated plywood. Spiral ligament, spiral lamina. Those two hold the basilar membrane tight between them, and the hair cells would be located right where my cursor is circling, right where my cursor is circling, right where my cursor is circling. And remember, you've got 1 row of inner hair cells all the way going up the cochlea. And remember that you've got 5 rows of outer hair cells at the apex of the cochlea, 4 rows of outer hair cells in the middle, and only 3 rows of outer hair cells toward the base of the cochlea. Good. And what's this thing called? Stria vascularis, the blood supply to the cochlea, to the scala media especially. Showing a close-up then of this particular picture, showing a scala media here. It's actually gives a nice picture of the way things move in the ear, which we will get to in the second half of this morning. We'll start talking about cochlear physiology, but this is showing a nice picture how the footplate of the stapes is pushing into the oval window, and follow the arrows is moving the fluid around and around, down through the helicotrema, down through the scala tympani, scala tympani, scala tympani to bulge the round window. The inaccuracy of this slide is that it shows you that the scala media actually gets smaller as you go toward the apex, which is patently false. This one here is showing it more correctly, okay? This picture here shows that inaccuracy too. In other words, that the scala media gets smaller as you go toward the apex, which just ain't true, okay? That's why I said same here. What's wrong with this picture? Spiral ligament, spiral lamina, spiral ganglia. All right, and the bony core of the cochlea, the modiolus. The modiolus. All right. Helicotrema at the very top. So here's a close-up of one coil. A close-up, scala vestibuli, scala tympani, I should say scala media, and scala tympani at the bottom. Reissner's membrane, basilar membrane held tight between the spiral ligament and the spiral lamina. And then you've got the spiral ganglia, the cell bodies of the eighth nerve fibers. The cell bodies of the eighth nerve fibers. And maybe we can show it to you here too, if I'm just remembering. Oh yeah, here. Here's the eighth nerve fibers, okay? So you've got cell bodies of the eighth nerve fibers from the vestibular system, cell bodies of the eighth nerve fibers of the vestibular system. But in the cochlea, the cell bodies are lined right up along, just at the edge here. Okay, right at the very edge where my cursor is. And that's what's being shown. Let's see. You can't really see it here. It doesn't show it. But here, these little white balls here, okay? Remember, please don't think you have 1, 2, 3, 4, 5, and 6. They're all around. This just happens to be a cross section. Same here, a cross section. Anyway, so spiral ganglia shown here. You can see the little olives, the little eyes looking back at you. This here would be these. Good. This is a closer up view. You're looking at the organ of Corti, tectorial membrane, supporting cells, basilar membrane, spiral ligament, like this big fan, spiral lamina, these two layers of bone, spiral ganglia, there's the eyes looking at you, the cell bodies of each fiber of the eighth nerve, outer hair cells, inner hair cells, and then we talk about the fluids. Perilymph, peri meaning around, okay, fills the bony labyrinths, scala vestibuli, scala tympani, and then endolymph fills up the scala media, opposite in chemical composition, but note carefully, see the walls of the hair cells? This little area that I'm circling here is kept secret and kept closed off from where I'm drawing my cursor right here. See that where I'm tracing here? All of this fluid here, endolymph, is kept separate from the fluid that bathes the walls of the cell bodies of the hair cells. And this fluid in here, do you remember from a couple of weeks ago, is called cortilymph. Cortilymph. And cortilymph is like perilymph inside the scala media. And that's how the hair cells are in contact with two opposite fluids. And you need that to create an electrical charge, because remember, that's what the cochlea does. It transduces motion of fluid into electrical current. And that's what the hair cells do. Now always remember, the inner hair cells are afferent, sending info to the brain. The outer hair cells are efferent, taking info from the brain. And we'll look more about that in cochlear physiology as we move on. Here's a very close-up now of the scale of the organ of Corti. Tectorial membrane, hairs on top of the inner hair cells, hairs or stereocilia on top of the outer hair cells. And remember, this fluid here is kept closed off from this fluid here. Endolymph is where I'm tracing here. Cortilymph is where I'm tracing here. Note that separate fibers go from the outer hair cells and run along the eighth nerve. And these are eighth nerve fibers terminating at the base of the inner hair cells. So inner hair cells are in cahoots with the eighth nerve. Outer hair cells aren't. The nerve they are in cahoots with is called the olivocochlear bundle. It goes from the low brainstem, the superior olivary complexes of the low brainstem, which we will look at more later on in this course, okay? Basically, all right, they run in the opposite direction. They're running this way to the outer hair cells. eighth nerve fibers from the inner hair cells go to the brain this way. So this is afferent, this is efferent. There's a trade-off of information. The outer hair cells are like little motors. They're like the muscles of the cochlea. And we'll look more in cochlear physiology as to how that works. Okay, but reviewing here, supporting cells, inner hair cells, outer hair cells, cortilymph fluid, endolymph fluid up here, tectorial membrane here. This picture complements this one. So this is just showing you the cups that are holding the outer hair cells and the inner hair cells. And again, these little golf tees emphasize, okay, the fact that the fluid here is kept separate from the fluid that bathes the stereocilia. So the fluid that touches the hairs is endolymph. The fluid that touches the walls of the cell bodies is cortilymph, which is perilymph inside the scala media. This is another view here looking at kind of a clear cross-section of the tectorial membrane and how it lays on top of the stereocilia. The stereocilia are arranged like W's, kind of like V's or horseshoes in the outer hair cells, and they're usually in a fairly straight line on the inner hair cells. Remember, the inner hair cells are like pears, like couch potatoes. They have a different shape, and their neurons are the eighth nerve fibers, and the outer hair cells terminate. The neurons that go to them are the olivocochlear bundle. Here they're drawing 3 rows of outer hair cells, so they must be talking about the base of the cochlea. This is a simple view of the organ of Corti, one that I just drew. Inner hair cells, outer hair cells, afferent fibers, efferent fibers, tectorial membrane. And note that the tectorial membrane does not touch the hairs of the inner hair cells. These hairs, however, are indeed embedded underneath. Okay, they are stuck in here. You'd have to tear this membrane off. Now here's a real human cochlea. Reissner's membrane, RM, scala vestibuli, perilymph, scala media, endolymph, scala tympani, perilymph, spiral ligament, SL, stria vascularis. Tectorial membrane has been torn off. This person obviously has died. Okay, tectorial membrane should be laying across the outer hair cells. No longer is. Again, it's all about hair cells. Reissner's membrane, spiral ligament, spiral lamina, spiral ganglia would be to your left. Can't see it here. Basilar membrane, outer hair cells, inner hair cells. Stria vascularis, spiral ligament. Inner hair cells have about 50 hairs on top of each cell. Here's one cell. Here's another cell. Here's another cell. Outer hair cells, here's one cell. Here's another one. Here's another one. And outer hair cells have about 100 stereocilia on the top of each cell. Inners have about 50 stereocilia on the top of each cell. And how many inner hair cells do you have in your whole cochlea? About 3,000. How many outer hair cells do you have in each cochlea? About 12,000. But you'd think there would be 9,000 because 3 times 3 is 9. But remember, as you're going up the cochlea, you start getting 4 rows of outer hair cells and then 5 rows of outer hair cells. That's why you have about 12,000 outer hair cells. Damage to the cochlea is usually confined mostly to the outer hair cells. And this is significant regarding cochlear physiology that we will be touching on in about 10 minutes from now. We're just doing a review of the anatomy. Here's another picture of inner hair cells, another picture of outer hair cells. Inner hair cells on the top, outer hair cells at the bottom. And now you can look at the test tube shapes underneath. See that? So that's one outer hair cell. See how you've got a lamina, or you've got some type of a thing that closes off, that pinches off the hairs from the cell bodies. So this would be cortolymph under here, and endolymph bathes the hairs. That's how the cell is in contact with different fluids. So a close-up of the top of an inner hair cell, the tall choir boys at the back and the short choir boys at the front. Here's the top of an outer hair cell. And again, the short stereocilia at the front, the taller ones at the back. How hair cells compare to hairs on a head, okay? A hair cell compared to a human hair, and don't forget you got 50 to 100 stereocilia on top of each cell. So here you're taking the hair cell, comparing it to the size of a human hair in gray. So we are talking tiny. And I showed you this picture before too, a blown up an electron microscope view of a bug with a gear in its claw. Bring it closer and you'll see a tiny white dot on one of the teeth of the gears. Bring it closer, that's a hair cell. Don't think of this as one hair, think of it as 50 or 100 hairs all clumped together because the hair cell is dead. And this picture is boring, so don't worry about it. I like this picture because it shows you that high frequencies are located at the base of the cochlea and low frequencies are located at the apex of the cochlea. The cochlea is tonotopic. Specific frequencies are represented in specific places. Also, the cochlea is tonotopic. High frequencies at the base, low frequencies toward the apex. Here's a picture of a spiral ganglion. You're looking at all the cell bodies of the eighth nerve fibers that would go this way and this way. Nerve cell bodies of the eighth nerve. Cell bodies are just like, when you think of cell bodies, just think of, I'll move it back here so you can see it a little better. Cell body is just, here, this. It's the cell. And then there's arms that stick out from the cell body, and that's the nerves, okay? Each nerve fiber has a cell body, and then the nerve fiber sticks out from each side of the cell body. That's all I mean, okay? Cell bodies, by the way, are gray. Neuron fibers are white because they're covered with fatty myelin. And when you think of fatty myelin, think of the rubber that covers an electrical wire. It's the insulation. People who are losing myelin are going to get multiple sclerosis. That's what MS is. Anyway, just talking. Okay. And we're getting near to the end of our anatomy PowerPoint. This is showing you inner hair cells and how they get most of the eighth nerve fibers. Each inner hair cell gets 10 eighth nerve fibers. Okay? And outer hair cells, how do they talk to the eighth nerve? Barely. About 10 outer hair cells share 1/8 nerve fiber. So really the eighth nerve fibers are mostly in cahoots with the inner hair cells. Okay, this is a picture showing you noise-induced hearing loss, high-frequency hearing loss, going down, and then these lines here are showing you when you unrolled this person's cochlea. This guy was a hunter, I guess, who died, okay? And you unrolled his cochlea and looked at the hair cell situation. And you've got outer hair cells fine and inner hair cells fine, and then all of a sudden in the high frequency area here, they're all dead due to noise. Noise-induced hearing loss. And this is a right-handed hunter. Okay, and when you hold a rifle with the right hand, it's the left ear that's going to be most exposed to the barrel and gets most of the noise. And so the hair cell damage is most pronounced in the left ear of this right-handed hunter. So noise is the second most common cause of hearing loss out there. Presbycusis, presby, the Greek word for old. Presbycusis is trouble hearing treble, and age is the first, that's age, hearing loss due to aging. That's the most common cause of hearing loss. The second most common cause is noise. And elderly in North America have worse hearing than elderly in Africa because elderly in Africa have less noise pollution than we do. So lots of our hearing loss is kind of like a combination of presbycusis and noise-induced loss. If you can hear someone's headphones and you're not listening to the headphone, imagine the damage. So if we share screen here again, only this time not looking at PowerPoint, but rather looking at notes, you'll see that we covered quite a bit of ground. At the start of the notes, we talked about the fluids being shared and that they both have hair cells. We didn't cover anything on the vestibular system, not in our review today, but please go and look at that from a previous pair of Zoom sessions. Cochlea is the Greek word for snail shell. Chinchilla cochlea has 2.5 turns. The human cochlea has chinchilla has 3.5 turns. We've got 2.5 turns. Don't worry about this dimensions. Basically, the cochlea is about the size of the tip of your pinky finger. Very inaccessible, buried deeply into the petrous portion of the temporal bone. Don't worry about knowing sodium versus potassium. Just know that the fluids are different. Know what fluid is in the bony labyrinth and what fluid is in the membranous labyrinth. Don't worry about ductus reunions, couldn't care less. Look at the scala, make sure you know what those are and what they are associated with. Okay, and then we have a close-up single turn of a cochlea, Reissner's membrane, basilar membrane, spiral ligament, stria vascularis, modiolus, spiral lamina, spiral ganglia, and then we talk about a close-up section of the scala media and all these little pieces and parts, tectorial membrane. Remember that the basilar membrane is narrower at the wide base of the cochlea, goes backwards to what you think. Don't worry about the names of supporting cells, but do know what cordylymph is. Okay, and we move on and look at some electron microscopy of normal versus damaged hair cells, and we did that too. So these numbers are good to keep in mind. That's very testable material. Keep going. Cochlea is tonotopic. Yep, you betcha. Okay, Helmholtz is the main one. High frequency hair cells located at the base. Low frequency hair cells are located at the apex. All right, stop sharing here. Let's go to cochlear physiology. Let's take a look at how this thing works, what it does. It's quite an amazing picture, really. So let's kind of go to our, I believe it's going to be Unit 6. That's where I'm going to be starting to dump some of this stuff, okay? So look at this unit here, cochlear physiology. The first half hour of what we did today was reviewing anatomy so that you could have somewhat of a piece of it and recall from earlier. And now let's look at cochlear physiology, which we will spend today and next week and maybe even the week after. Who knows? Let's look. Let's just go there now to see. Share screen, and make this one smaller. Here, let's go to here, inner ear physiology. Have a look. There's your readings for it, chapter 3, pages 80 through 92. The purpose of the vestibular system is to give your brain info about your body positions in space. Balance. The purpose of the cochlea is to change mechanical energy from the middle ear. Remember, the middle ear changes sound into mechanical energy. The cochlea has two things it does. It changes mechanical piston-like energy from the footplate of the stapes, moving in and out of the oval window, and it changes that into hydraulic fluid energy because the fluids are moving in the cochlea. And then the hair cells change the fluid motion into electricity. So in the cochlea, there's two transductions, mechanical into hydraulic and hydraulic into electrical. Hair cells are what we call pilloried mechanoreceptors. They're pinched off at the necks, in other words. So they're pilloried because they're tied around the bottoms or fixed at the bottom and tied around the necks. Okay, the stereocilia are in contact with endolymph and the cell bodies are in contact with endolymph. I should say cordylymph. Okay, now read the paragraph. What happens when the footplate of the stapes pushes in and out of the oval windows? It creates traveling waves in the cochlea. Now I'll stop sharing for a second. Traveling waves are like water waves. They do go up and down. Okay? Sound waves we called longitudinal, remember? The motion of the wave is parallel to the squeezing. Condensation, rarefaction of molecules. We drew that as up and down because it was easier, remember? Okay. Traveling waves really do go up and down. So traveling waves are transverse. And the pushing in and out of the oval window causes waves of motion. And what moves, really? It's the basilar membrane goes up and down. The whole scala media goes up and down. Remember, it's the membranous labyrinth, so it can bend. So what happens if a high-frequency sound hits the middle ear, hits the eardrum, and the footplate of the stapes is going really fast because it's a high-frequency sound? That's going to cause a traveling wave ripple along the basilar membrane that will stop right at the base. In other words, the wave won't go far. It's going to go and stop, and it's going to wiggle the basilar membrane right here at the base of the cochlea. If it's a low frequency sound hitting the eardrum, wiggling the middle ear ossicles, pushing the footplate of the stapes less frequently because it's a lower frequency sound, the traveling waves of the cochlea will go way up the cochlea. It'll turn around, it'll go up the coils of the cochlea. The basilar membrane will ripple, but the peak of that wave, the highest part of that wave, will stop at the apex of the cochlea. So a high frequency sound, the peak of the wave will stop right at the base. Mid frequency sound, halfway up. The bass sound, okay, the cochlea is tonotopic because specific frequencies are represented in specific places. And waves created in the cochlea are going to stop either at the base or in the middle coil or at the top coil. It all depends on where the waves stop. And those are the hair cells that are stimulated. So let's read what someone very famous said about how the traveling wave excites the cochlea. All sounds entering the cochlea, and really sounds don't enter a cochlea. Sounds create traveling waves in the cochlea. So take that word with a grain of salt, okay? All sounds, you should say, that stimulate the cochlea. And why do we say sound waves can't get in the cochlea? Because a 250 hertz tone is 4.5 feet long, remember that? Wavelength is speed of sound over frequency. Frequency is speed of sound over wavelength. A 250 hertz tone is 4.5 feet long. The cochlea, when you unroll it, is 3 centimeters long, or barely more than an inch long. So sound waves don't get in a cochlea. Sound waves create traveling waves that activate the cochlea. And traveling waves are way shorter than the sound waves. Okay? Good. Now, share screen once again. All righty. All sounds activating the cochlea travel in a ripple wave along the basilar membrane. So say all sounds activating the cochlea create a wave that ripples along the basilar membrane from the base to the apex. The waves go very much slower than sound does in air, taking a few milliseconds to complete a journey of a few millimeters over the sensory hair cells. Each individual frequency component wave grows in intensity as it travels, gets taller, in other words, eventually reaching a peak before coming to a complete stop at some unique place along the basilar membrane. And wherever that peak stops, if it stops at the base, you heard a high frequency, because it was the high frequency hair cells that sent the message to the brain. If the wave stopped at the apex, it stimulates the low frequency hair cells at the apex, and you've heard a low frequency sound. So now that's written by a guy named Kemp. And Kemp is still living, and Kemp discovered what is called OTO, ear, acoustic, sound, emissions, sounds coming out of the ear. Doo-dee-doo-doo. Don't confuse this with ringing in the ear. That's tinnitus. Tinnitus is subjective. Only the person who has it hears it. Otoacoustic emissions can actually be measured with a probe, and they result from the outer hair cells working their proverbial butts off. Remember we said the outer hair cells are the muscles of the cochlea? They don't communicate much with the eighth nerve. They don't send sound info to the brain. It's the inners that do. If you lose inner hair cells, you're deaf. If you lose outer hair cells, you'll have a hearing loss. It's different. We'll be explaining all of this, okay? But outer hair cells, because they are always stretching and shrinking, you know why they stretch and shrink? They're helping the inner hair cells pick up soft sounds. Inner hair cells can only pick up sounds from about 50 decibels up to about 120. Inner hair cells by themselves can't pick up 10 dB, can't pick up 20, can't pick up 30. They need at least 50 dB to sense the sounds. The outer hair cells help the inner hair cells pick up soft sounds, and they do so by stretching and shrinking. We'll talk more about that. But when you work really hard, what do? You sweat. Sweat's a byproduct of your work. Well, otoacoustic emissions are a byproduct of the outer hair cells working their butts off. So we'll talk more about that later. Boy, the dogs upstairs are going nuts now. Sure tell that. Wow. Okay. Let's look at some names here. You got Kemp, you got a guy named von Bekesi, and you got a guy by the last name of Gold. Okay? Von Bekesi was a Harvard researcher. Let's go to the PowerPoint for this particular unit. Here we go. Look at this guy, Hermann von Helmholtz. Hermann von Helmholtz was the guy that discovered that hair cells are located in specific places. He is the one that discovered that high-frequency hair cells are located at the base of the cochlea and that low-frequency hair cells are located at the narrow apex of the cochlea. Hermann von Helmholtz. Okay, but he didn't know how it was done. He didn't know he didn't know about traveling waves. He just knew that, oh, the basilar membrane is wider at the narrow apex, so it's got more mass. Perhaps the cochlea resonates with low frequencies there. And the cochlea resonates with high frequencies at the base of the cochlea because the basilar membrane at the base of the cochlea has less mass and it's more stiff. So he discovered that. Remember, mass resonates with lows, stiffness resonates with highs. Never forget that, okay? So the scala media at the apex of the cochlea has more mass and is less stiff. Therefore, it's going to resonate with lows. The scala media and the hair cells at the base of the cochlea has less mass and is more stiff. The walls are more stiff. So it's going to resonate with high frequencies. And it was Hermann von Helmholtz who discovered that. Next slide, this guy, von Bekesi. Yep, there's no E after the G here. George, that's the way Hungarians spell it. He was Hungarian, okay? Remembering George von Bekesi from 1899 to 1973, so I guess he passed away at age 74. He discovered the traveling wave. He discovered that the wave of motion, the basilar membrane makes a wave, a ripple. And it's that ripple that we call the traveling wave. It's that ripple that is actually a transverse wave. The up and down is perpendicular to the direction the wave is moving, like water waves. It has a ripple to it. And it's wherever that ripple stops, that's what hair cells are sending info to the brain. It's at that area. George von Bekesi. Here's another, guess what? He even won a Nobel Prize for his discovery of the traveling waves of the cochlea. So here's a stamp out of Sweden, only in Swedish they call it Sverige, okay? George von Bekesi, Nobel Prize, 1961. And look, they're showing semicircular canals, cochlea, membranous, bony labyrinths, actually won a Nobel Prize for his discovery of the traveling wave. Here's another picture of him, okay? George von Bekesi. Now here's Gold. Now Thomas Gold was ahead of his time. Let's read this. If the term ahead of their time applied to anyone in auditory research, it applied to Thomas Gold, who died this June this year, well, that was 2004, at age 84. Gold is widely celebrated as a cosmologist, wow, guy who looks at stars, geophysicist, an original thinker with major contributions to the theories of the origin of the universe, nature of pulsar stars, physics of the magnetosphere, all kind of extraterrestrial origins of life on Earth. Yikes. The guy was a bit of a theorist. But for just a few years, between 1945 and 1950, now, those are the years that von Bekessy discovered the traveling wave. He was a Hungarian refugee who got taken in by the United States, and he had his PhD, his post-hole digger degree, his doctorate of philosophy of whatever, and he got hired at Harvard University. He was a physicist, and his whole interest was the ear. So he did a lot of work on cadavers, because in those days, I'll stop sharing, they didn't have CAT scans, they didn't have MRIs, you couldn't do all the stuff we do now. He discovered the traveling wave in dead people's ears. Okay, he would put 120 decibels into the dead guy's ear, and with the head cut open and all that, he looked at waves that took place. So, that's the only way that he could see any of this. That's how he discovered it. Gold had a unique theory, and Gold said, but outer hair cells look so different from inner hair cells. Maybe the outer hair cells are doing something different than the inner hair cells. Maybe they're not all just sending info to the brain. Gold is the first person who suggested that the traveling wave might have something to do with outer hair cells as well as inner hair cells. Gold said, hey, outer hair cells look like thin test tubes. Inner hair cells are fat pears. So if they look different, they probably do different things. Now, let me tell you a little story here so that we're not all talking from notes. I'll just tell you this, okay? Von Bekessy made a great big model of the cochlea in his laboratory at Harvard University. And he had an oval window in it and a round window in it. He had a scala vestibuli, a scala median, a scala tympani. He had a tight basilar membrane, and he had all the stuff made in this great big cochlea. And then he would tap on the footplate of the stapes, the oval window, and he would create waves and look at these waves to back up what he was seeing in the cadavers. And it would work a bit, but it didn't work great. He found out, you know what? If I hit the round window, I get way better waves. I wonder why. Maybe God put these stapes of the foot the footplate of the stapes in the wrong window, because my model works way better when I put the footplate of the stapes into the round window instead of the oval window. Gold said to him, you know what, those outer hair cells, maybe they increase the size of the traveling waves, and that might be explaining what your model isn't explaining. Your model is showing you traveling waves, but they're not big enough, are they? Maybe the outer hair cells in a living person actually do something to increase the size of the traveling waves. And von Bekessy said, no, I don't believe that. I won the Nobel Prize. You go home. So Gold did. He just left the field. And Kemp, some 30 to 40 years later, found these things called otoacoustic emissions. And these were sounds coming out of the ear. In other words, backward traveling waves, hitting the footplate of the stapes, wiggling the ossicles, and making the eardrum work like a speaker. And otoacoustic emissions are, where do they come from? And Kemp discovered they couldn't come from anywhere other than the outer hair cells, because if we kill off the outer hair cells, there's no more OAEs, no more otoacoustic emissions. So they have to come from the outer hair cells. So Kemp phoned Gold and said, you were right. I found these sounds coming out of the ears, and they are a byproduct of the outer hair cells increasing the size of the traveling wave. So Kemp vindicated Gold. So that's the general story about what took place here. So here's a picture of gold once again. And let's read what it says. For just a few years, right after Second World War, Gould was deeply engaged in state-of-the-art auditory research in Cambridge, England. And there he recorded fine frequency tuning of primary auditory neurons, in other words, the eighth nerve fibers, and began conducting penetrating experiments on human frequency discrimination, what we covered this morning in 110, difference Lyman, or just noticeable difference, or delta F. Okay, the ability to distinguish frequencies close together. That's another thing Gould said about the outer hair cells. Not only do they amplify the size of the traveling wave, but they also sharpen the peak of the traveling wave. Not only do they make the wave taller, like von Beckesy's model didn't show, okay, but they also make the peak, instead of being rounded, they force it into a point. And when they force the peak into a point, you've got more fine-tuned cochleas. You've got a better ability to distinguish frequencies close together. Your frequency resolution goes up. Your delta F doesn't have to be as big for you to notice a change in frequencies. Okay? There's a twofold role of what the outer hair cells do. They amplify the traveling waves so that the inner hair cells can pick up sounds less than 50 dB. And secondly, they sharpen the traveling wave, the peaks, so that the cochlea is more fine-tuned to different frequencies. And then we'll see more of that next week as well. Well, I'm just giving you a preview of where we're going here, okay? He boldly challenged von Beckesy's interpretation of cochlear mechanics. He was the first to propose an active cochlear process, in other words, outer hair cells, involving electromotile, in other words, movements, to enhance the cochlea's response to sound vibration, to make the wave bigger, and to predict and search for spontaneous otoacoustic emissions. Weird, huh? This is a picture of Gould soon before he passed away. Thomas Gould center-facing camera. Okay, in the late 1940s, he suggested mechanical resonators inside the cochlea, talked about outer hair cell motility and otoacoustic emissions. This photograph was taken in 1988, toward the end of his career. Here's Kemp, younger than Gould, and he found otoacoustic emissions that proved that Gould's theories were right. So let's look at this picture here. It's kind of interesting. We talked about this a little bit in cochlear anatomy when I showed you a couple of those pictures of the cochlea. Let's look at these here. Because what you're seeing here is, on the left, red arrows and green arrows. And the red arrows is motion of fluid going through the scala vestibuli. Scala vestibuli, scala vestibuli, SV, SV, FD. Down through the helicotrema, scala tympani, scala tympani, scala tympani, scala tympani, scala tympani, to bounce and hit the round window. So the oval window is associated with scala vestibuli, the round window is associated with the scala tympani. This is showing you a closer up shot. But see, notice how the arrow going in and the arrow going out create this bulging. See how the Reissner's membrane gets dented in and the basilar membrane gets dented down? That's the traveling wave. Because fluid simply going in and out of the cochlea isn't going to make anything go up and down. It would just be going back and forth. How does that back and forth movement translate into an up and down movement? That's the trick to understanding the cochlea. You've got the footplate of the stapes pushing in and the round window bulging out. I'll stop sharing. The footplate of the stapes pushing in and the round window bulging out. Boom, 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 boom. Okay? That's what I call the horizontal movement of fluid in the cochlea. But the horizontal movement of fluid in the cochlea, how does that translate into an up and down movement of a traveling wave that's going to stop either at the base or at the middle or at the apex? This is the key. Let's look at this today, and then we'll be done our session for today. That's a sideways picture. Here's how it happens. Here's a cochlea unrolled. The cochlea is completely unrolled. Oval window, foot plate of the stapes, round window, okay, that bulges out. Here you're looking at the stapes foot plate on top. This stapes foot plate is this little black thing here, okay? Now you're looking at a cross section of the cochlea, and this is just a schematic. But what do you call this area here by the arrow? What's scala? Scala vestibuli. What is this? Scala tympani. And what's the black line? Scala media. So if you take a cross section, yep, and you turn it sideways to face you, you're looking here. Scala vestibuli, scala tympani, scala media. Why does movement going back and forth result in an up and down motion inside the cochlea? And this up and down motion might occur here. So you can see that traveling wave. Or the traveling wave might be here, or it might be here, all depending on the sound that activated the cochlea. How does that work? Well, look at how the cochlea gets narrower. And it's this helicotrema. Helicotrema, la, 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 la. Look at the helicotrema. It's narrower. So when you're pushing fluid in this area, it's going to build up pressure because it's getting narrower here. So there's a buildup of pressure of fluid because the cochlea gets narrower. And that buildup of pressure has to be relieved someplace, because if it weren't, this foot plate couldn't push in and out. So what gives is the membranous labyrinth. What gives is the membranous labyrinth. And that is how an up and down vertical motion is made from a horizontal fluid back and forth motion of the scala vestibuli and scala tympani. The scala media is caused to go up and down because of the buildup of pressure. The cochlea gets narrower toward the apex, and this fluid has to squeeze around here. Okay? Here's another picture showing you an unrolled cochlea. So they're showing you how the scala vestibuli gets narrower and narrower toward the helicotrema. Boring picture. You saw this in anatomy, so we no need to cover that. Saw that in anatomy, no need to cover it. But here again, foot plate of the stapes pushing the oval window, and then you've got that helicotrema. A build-up of pressure here results in an up and down motion here. Okay, and that horizontal movement can be seen by these arrows and these arrows. The vertical motion is shown here by the indentation of Reissner's membrane, indentation of basilar membrane, and even the tectorial membrane. The whole thing gets activated, and that's how the hair cells get activated, either here or here or here. It just depends on where that up and down motion took place. Did it take place at the base, the middle, or at the apex? Here's another picture showing you basic cochlear physiology. Eardrum, malleus, incus, stapes, foot plate, oval window. Look at the horizontal movement. And look, you might have an indentation here or an indentation over here. Who knows? This is kind of a weird looking picture because you've got the scala vestibuli in pink, and then you've got the scala tympani in green, or here. Okay, scala vestibuli here, blue. Scala media is pink. Scala tympani is blue. And look at this big bottom here. This must be the hair cells themselves, or supporting cells. And then these are the stereocilia of the hair cells, and here's the tectorial membrane laying on top of the stereocilia. Okay, but it's all to show you once again horizontal movement being changed into vertical up and down motion, and that vertical up and down motion may take place here or here. Wherever that wave stops, that's when hair cells are stimulated. Once again, another picture showing you the same thing. Movement of sound vibrating changing sound into mechanical energy, pushing the stapes in and out of the oval window, creating hydraulic energy, and that hydraulic energy creates traveling waves, okay, which may end up who knows where in the cochlea depending on the sound that comes in. Here this picture's even called cochlear horizontal and vertical action. And the only reason you got vertical action resulting from horizontal action is due to the buildup of fluid from the wider end having to go around the narrow helicotrema. Okay, let's look at our notes now and see what we covered, and then we're done. Notes. Here we go. So how does the traveling wave work? Horizontal and vertical motions in the cochlea cause inner hair cell stereocilia to bend or shear at some location. Cause inner hair cell stereocilia to bend or shear. To bend or shear. The movement of that scala media up and down at some unique place along the basilar membrane, whether the base, the middle, or the apex, is going to change this still motion into this. And see how the hairs are bent now? The way to best explain it is, don't think of it doing this. Think of it as doing this. Okay, if I had elastic bands between my fingers. And let's show you in another picture here. See how there's two hinges? One here, one here. When the whole thing gets bent, it's necessarily going to bend the hairs. Here's another picture. One hinge here, another hinge here. At rest and when activated. Okay, so when the peak of the traveling wave stops at some place, that's where this top thing happens. And it's when those hairs are bent, a message is sent up the 8th nerve to the brain. That's basic cochlear physiology. Share screen now and look at our notes. And just review here. Horizontal and vertical motions in the cochlea cause inner hair cell stereocilia to bend or shear. Yes, you may have seen outer ones bend as well, but it's the bending of the inners that sends the info to the brain. The sheared stereocilia cause neural message to be sent from inner hair cells along 8th nerve to the brain stem. The horizontal movement results in, not on, in vertical movement, which is the traveling wave. Horizontal is the movement by way of the oval window to the helicotrema and around to the round window. The vertical is the indentation of Reissner's and basilar membranes, the walls of the scala media. How does this happen? Cochlear fluid, perilymph, can't be compressed much, so as the stapes footplate moves in, the round window bulges out. The scala media displacement, however, occurs, that vertical movement, because of the narrow helicotrema. As stapes is pushed into the oval window, the narrow helicotrema resists movement through it. Perilymph pressure increases in the scala vestibuli. This pushes the scala media, Reissner's, and basilar membranes down. As the stapes moves out of the oval window, the narrow helicotrema resists movement through it. Perilymph pressure increases in the scala tympani now, pushing the scala media up toward the scala vestibuli. Stapes, unrolled cochlea and cross-section. The highest amplitude of the wave indents the whole cochlear duct, read scala media, at some specific point. But in pictures, it's often easier to illustrate only the basilar membrane movement. The basilar membrane is the floor upon which the hair cells stand. Think about it as that. Indentation shears the stereocilia at some particular place along the basilar membrane. The mechanical vibratory pattern of the basilar membrane is very stable. In other words, it has more mass at the apex and less stiffness, more stiffness at the base and less mass. Changing the fluids, nothing really alters it. Recall the basilar membrane is wider and less stiff, more flaccid at the narrow apex. It's narrower and stiffer at the wide base. High-frequency traveling wave therefore stimulates basal high-frequency hair cells. Low-frequency traveling wave is longer, and its peak is more toward the apex, stimulating apical low-frequency hair cells. Intensity affects the size of the traveling wave. Textbooks exaggerate the motion. Its movement really is very tiny. Von Bekesi had to stimulate cochleas with 120 dB SPL to actually see anything. This is where we'll stop. This is where we stop today. Next week we will continue on from here. So this is the introduction to physiology and the review of the anatomy. I will put this unit, well, in Unit 5, I guess, cochlear physiology in 120. I'll stop sharing now. And I'll stop recording now.